All right, so we're going to finish up this week with 8.4, which is on 2 more operations you can do if you write complex numbers in trig forms. We've done multiplying, we've done dividing. We're going to look at raising to a power, and we're going to look at taking a root. Now, we're not going to technically prove the formula to raise it to a power. We're going to do one specific example, like squaring. And then my hope is that you notice a pattern. All right, so let's take z, which represents a generic number in trig form. I don't know the radius or the specific angle, but whatever it is, we're going to represent it as r and theta. And we're going to square them. So just to visually make it easier, I'm going to write another copy next to it, because you need to visualize the distributive property. Okay, so z is what's written in black. What's in red is just pretend like that's invisible, but it's there to help you do this. Right? So if you want to square z, you've got 4 terms you need to multiply together. 1, 2, 3, and 4. Well, terms 2 and 4 have to be FOILed because they're binomials. They have a plus sign. Terms 1 and 3, those can just be multiplied the way they are. So we could just do 1 times 3 and write that down. So let's start multiplying all this together. What's 1 times 3? What's r times r? Yep.
R squared.
That's r squared. Okay, and if you think, well, how could it be r squared? Well, you could rearrange this. Just imagine putting this r over here. And if you want to erase it from there. So it's r times r, which is r squared. Now you've got to FOIL the rest of this out. So Hannah, what's cosine times cosine?
Cosine squared.
Cosine squared theta. And Sean, what's cosine times I sine?
I sine. That is cosine I sine.
Yep. What's your answer?
Cosine times I sine.
Just cosine times I sine. And then we have cosine times I sine again. So Brianna, how many of those cosine times I sines do we have?
2.
2. So we have 2 of the cosine I sines. Now I wrote it in a little bit different order. What I did, actually, you know what? I'm even going to do it like this. What I did there is fine. It's all multiplication, so I'm just changing the order. We have 2 of the cosine times I sines. I'm just saying sine I instead of I sine. Same. All right, so we've got that. And the last thing we have is I sine times I sine. Well, it's a positive times a positive. So, Andrew, what's a positive times a positive?
Positive.
That's a positive. And Justin, what's the I times I going to give me?
I squared.
So we have an I squared. We'll come back to that. And Gracie, sine times sine?
Sine squared.
Sine squared. Okay, let's see what we can do with that. What's I squared? Yep.
-1.
Okay, so let's just, I won't rewrite it, but I'm just going to kind of cross this out and put -1 times sine squared, and I'll rewrite it. So now we've got r squared okay, cosine squared plus 2 cosine sine minus sine squared. Now, I want to just kind of look at what's happening here. You've got a cosine squared minus sine squared. That's something special. I could rearrange it and put it next to it if you want to see it that way, but it's the same thing. Cosine squared minus sine squared. Does anyone remember what that is? And it's not sine squared plus cosine squared equals 1. That's a little different. But cosine squared minus sine squared. It's a double angle identity. Yep.
Sorry, this is off topic. It doesn't have to do with the question. But where did the I go that's next to the first sign?
It was I squared, so that's -1. I squared always turns into negative.
No, but there's also
No,
an
there's
I
the
next to
sign.
sign.
Oh, yeah, this side. It's right there.
Okay.
Yeah. It was in black. It just didn't show up. That's all. Now it's there. Thank you. So, yeah, now we've got this cosine squared minus sine squared. Anyone remember what that is? Yep.
Cosine 2 theta.
Yeah. Cosine squared minus sine squared turns into cosine 2 theta. All right, let's do that. So we have r squared cosine 2 theta plus, I'll put my I down right away so I don't forget. And look at this part. 2 cosine sine. Well, that's something else. 2 cosine sine. That turns into sine 2 theta. Any question on that? I know I have 2 cosine sine, and this says sine cosine, but it's the same thing. So 2 cosine sine turns into sine 2 theta. And that's what you get if you take z and raise it to the second power. So now, without going through all the work of foiling again, I want to see if you can look at the pattern that we got and tell me what z cubed would be. If it follows a similar pattern to the one above, anyone have a guess what you would get? Yep, Trevor?
Would it be r cubed cosine 3 theta
Yep.
plus I sine 3 theta?
Yeah, no, we didn't prove that, but that is the pattern that ends up happening. So when you want to raise a complex number to a power, if it's in trig form, all you have to do is 2 things. And these 2 things are what we call DeMoivre's theorem. So you've got a complex number in trig form, and you want to raise this to the nth power. Now, this whole theorem is dependent on you already having the number in trig form. If it's not in trig form, you need to do that first. Once you get it in trig form, you do 2 things. You take your radius and you raise it to the power. You take your angle and you multiply it by the power. So like if you had to raise something to the 5th power, it would be r to the 5th cosine 5 theta, I sine 5 theta. And that's going to make raising things to powers a lot easier than having to do it in standard form. In standard form, you're going to have a ton of distributive property you'd have to do. Now, just squaring something, that wouldn't be that bad. But if you had to raise something to like the 7th or 8th power, you're talking about writing 7 or 8 sets of parentheses and then doing every FOIL in all of them. Probably make a mistake. So this is a lot easier. And you're only going to ever have to worry about raising to integer powers. We're not raising complex numbers to like 2.7. We're not doing that. Yep.
Could you go back first?
So the first example we're going to look at involves cubing a number. Now, cubing wouldn't be too bad if you didn't know this theorem. Okay, cubing would mean you'd have to take this, you'd have to write this out 3 times, and then you'd have to do all the foiling. I would foil the first 2 together first, get that answer, and then foil it to the last one. But that's not how you do it with DeMoivre's theorem. in order to use DeMoivre's theorem on this problem, what's the first thing I have to do with that number? Yep,
Get it into trig form.
I gotta get it into trig form. So this is when I said we'll practice writing numbers in trig form a little more today. Well, now we're gonna do that. What are the two things that you need to write a number in trig form? Yep.
The angle and the distance from the origin.
Yep. So we need the radius and we need the angle. So let's start with our radius. In fact, I think we did this one in the homework, or maybe the opposite of it. So you're going right 1, and then up square root of 3. What would be the radius of that point? Yep. 2. Yep. So your radius is 2. And your angle, we're in quadrant 1. Do I have to add 180 to my answer? Yeah? No. We're just going to do inverse tangent of, can someone remind me? What is it? Inverse tangent of what? Yep. Y over x. So really, it's just the inverse tangent of root 3. And when you do that, you're going to get 60 degrees. You can double check if you need to. But again, that's a common angle because it's a multiple of 30. Alright, so there's our angle. Now, write your answer out in trig form and then use DeMoivre's theorem. So 2 cosine 60 plus I sine 60. And we're raising that to, I think it was the third power. Okay, so now this part's easy. What's my radius going to be when I raise that number to the third power? Yeah.
8.
8. It's going to be 2 cubed cosine. And what's my angle going to be when I raise that to the third power? Sean?
180.
180. And that is the final answer in trig form. Now, let's practice something that we also did a little bit in the homework. Sometimes they wanted the answer in standard form. Well, standard form, we just do this out. But these are angles that are multiples of 90, so we should be able to do cosine 180 and sine 180. You really shouldn't need a calculator for that. So think about 180, and cosine is the x value. What's the cosine of 180? Yep,
-1.
-1. Good. So -1 plus. Now let's do the sine of 180. Sine is the y value. What's the y value of that coordinate? Yep.
0.
0. I times 0 is gone. And what would I be left with for my final answer? Negative 8. 8 times -1. That's the final answer in standard form. It is important that you know how to convert from trig to standard and from standard to trig. We did both in that problem. All right. Any question on that? Yes.
So you cube the imaginary number, right? How does it become, is the -8 not imaginary anymore?
So what step are you looking at?
Well, just the entire problem itself. You raise the first part, what you're given, you raise it to the power of 3,
Two to the-
higher than that.
So yep, 2 to the power of 3, and that's how I got the
No,
8.
not that. I mean the 1 plus root 3i. at the like top problem.
Yep.
So when you cube it, does it just become like a normal number and not imaginary anymore?
That doesn't always happen, but in this one it would, yeah. Yep. I'm not going to do all this out, but if you do it, yes, the I would disappear. Maybe you'd end up with like a plus 3i and a minus 3i, and then they cancel. Or something like that. Yep. So all the imaginaries would disappear in this one. It's a lot easier that they see they disappear right here when you just do I times 0, and you see it wipes it out. Yep. Now let's try this one. So let's do, so negative root 2 over 2 plus root 2 over 2i. Now this one would be even worse if you didn't use DeMoivre's theorem. Okay, you're not going to easily write that out 8 times and FOIL it. It's going to take too long. So let's change it to trig form and then go from there. All right. What quadrant is that point going to be in? Hannah?
2.
Yep, it's going to be in quadrant 2. And how does the amount that we're going to go left compare to the amount we're going to go up when we graph that point? It's the same. Okay, root 2 over 2, that's about 0.707. Negative 0.707, positive 0.707. So what kind of triangle? It'd probably be a little more like this. I messed it up a little. We went left 0.707 and then right 0.707. So not quite -1, +1. What kind of triangle would that be if you go left and up the same amount? Yeah?
Isosceles.
Yeah, it would be isosceles, which means each of these angles is how much?
45.
45. So you don't really even need to go through the inverse tangent. You know that this angle right here is a 45. So how much is this angle to get there? John?
135.
135. If you didn't know that, you could do the inverse tangent of y over x. But y and x are the same, except for this negative. So when you divide them, y divided by x, you get -1. And if you do the inverse tangent of -1, you're going to get -45. But that's not your answer because you need to add 180. So if you add 180, you get what Sean just said, 135. All right, now to find the radius, we're going to do Pythagorean theorem on this triangle. So square each leg, add them up and take the square root. What do you get when you square -√2 over 2? Yep. Well, when you're squaring something, it's always, what kind of number?
Oh, it would be just 2 over 4.
Just 2 over 4. Yep. So when you square the first one, you get 2 over 4. How about when you square +√2 over 2? What would you get? Yep. 2 over 4. So square each side, add them up, and then take the square root. So what's your radius going to be for this one? Yeah? 1. So now we can write our original problem in trig form. 1 cosine 135. I sine 135, and raise that to the 8th power. All right. Gemma, when I raise that to the 8th power, what's my radius going to be?
Just 1.
Just 1. It's 1 to the 8th power, so it just stays as 1. And we might need a calculator for this part, but how am I going to find my angle? We're gonna multiply.
1080.
Yep, so we get 1080. Now, 1080, that's a pretty big angle. Chances are they're going to want you to write the angle to be smaller than that. So what can you subtract from an angle? Whenever you can do this anytime you want, and it'll have no effect on the sine or the cosine. Yep.
360.
Yep, we can subtract 360. So let's do it once, and then you could do it 2 more times and get an angle of 0. So when you raise that number to the 8th power, that's what you get in trig form. And then in standard form, what's the cosine of 0? 1. Plus, what's the sine of 0? 0. So again, the imaginary part wipes itself out. It doesn't always happen, but it did this time. And what are you left with for a final answer? Yep, 1. That's the final answer in standard form. 1 plus 0i. That's the final answer in trig form. Okay, any question on that? So that's how you raise a complex number to a power. Now, think back about example 1 for a second. In example 1, we took something and cubed it. How would you undo that? If you took a number and you cubed it and you wanted to change it back to what it was originally. Yep.
You like do it the cube root.
You would cube root it. Okay, so in this case, cube root. That's how you undo cubing. So if I go back to example 1, if I took this number and I cube rooted it, it would bring me back to what I started with. So in other words, this is the cube root of -8. And if you're like, well, wait a minute, isn't -2 the cube root of -8? Yep, it is. Cube roots have 3 answers. Okay. -2 is an answer. That is an answer. And 1 minus root 3i would be the other answer. The nice thing that happens with imaginaries is anytime you get an answer that's imaginary, and I think we've said this before, they always occur in conjugate pairs. So if you know 3 plus 7i is an answer to your problem, then so is 3 minus 7i. Automatic. So complex roots always occur in pairs, conjugate pairs. So let's look at this one. So if you take root negative root 2 over 2 plus root 2 over I, you raise it to the 8th power, you get 1. Well, if you take the 8th root of 1, one of the answers that you would get is that. 1 is another answer you would get, so is -1. There's 8 answers. So that's, when we're dealing with roots, there's always going to be as many answers as the root you're trying to find. Cube root 3, 5th root 5, 12th root 12. Okay, so a lot of answers. On the test, you really don't have to expect to do anything more than like a 4th root. So you'd be looking for about 4. And once you get 1, the other ones are very easy to find because there's a pattern to them. But just getting the first one can be a little tricky. All right. So I basically just said that to you. In example 1, if you take the cube root of our answer, it gives you back the original problem that you started with. So when you're trying to solve something like, let's say I wanted you to find, just think about real numbers, the square root of 16. Square root means it has to do with a 2. The equation you would set up if you were trying to explain to somebody how to solve a problem like this is you'd say, well, that means that something to the second power is going to give you 16. And if you can figure out what you raise to the second power, which in this case it's 4, then that's the answer to the problem. Right? If I said, find the cube root, or we could say third root, because eventually we're going to run out of words. Like fifth root doesn't have a special name. We just say fifth root. So find the third root of 64. For somebody that didn't understand what that meant, I would say, okay, well, think of it as an equation. It means solve this equation. Figure out what you can raise to the third power and get 64 as the answer. So if I said to you, find the nth root of something, this is the equation you're solving. Find the nth root of A. That means that there's some number you can raise to the nth power and get A as the answer. Just like I showed you with square root and cube root. So this is the basic equation that we're going to set up every time. This and this represent complex numbers. I thought I wrote that somewhere. Z and A are elements of the complex number system. Yeah. Right, so Z and A are going to represent complex numbers. The key to being able to take roots of complex numbers is trig form. You have to write it in trig form. If it's in standard form, it's not going to work. It's not really doable. So we're gonna do it in trig form. Now, if you happen to be solving this type of problem, where it's basically asking you to find the fourth roots, we don't have to graph them, but just find the fourth roots of 1. For some reason, they don't say 1 in our book. They say that. If it's any other number, like find the fourth roots of 2, they would just write it out like that. Find the fourth roots of 2. But anytime you see find the whatever root of 1, they're going to replace the word 1 with unity. I don't know, that's just what they do. So if you see a question that says find the fifth roots of unity, it just means find all the fifth roots of 1. And remember, you're looking for 5 answers. Okay, 5 different answers. So I think what I'm going to do is, rather than write down all the steps, we kind of went through the steps in the last class and we did an example at each, like showing the step in an example. I think we'll just do a whole example and see how that works. I'm not going to show you all the steps. Let's just do an example. So here's your equation you want to solve. You're trying to find the fourth roots of 1. That means that there's a number, or numbers, you can raise to the fourth power and get 1 as the answer. So I said the key here is to write this whole equation in trig form. You don't have to worry about the 4. The 4, that's just an exponent of 4. That can stay the same. This is not trig form, and neither is this. If it was trig form, I'd be seeing sines and cosines. So what you do with the z on the left, and this is what you do in every problem, it doesn't matter what root you're finding, you always change z to this. R cosine theta plus I sine theta. Because your goal in this problem is to solve for z. Z is a complex number. We're going to be solving for z in trig form. What's the answer for z? I don't know. That's what we're trying to find in this problem. But once I do find it, I know that it's going to have a radius, and I know it's going to have an angle. I just don't know what the radius and the angle are yet. So that's how I'm going to represent it. So always change z to that, and you're going to solve for the r, and then you're going to solve for the theta, and that'll be your answer. Now on the other side, you're going to write that in trig form, just the way we learned yesterday. So this is 1 plus 0i, if you want to think of it that way. There's no imaginary part to this one. So graph that point. What's the radius of that point when you graph it? Yeah. 1. So the radius is 1. And what's the angle of that point? Yeah.
Would it be 0?
0. The angle is 0 degrees. So this right-hand side we just wrote down, this is different in every problem. You have to graph your point and find the radius, maybe using Pythagorean theorem, and find the angle, possibly using inverse tangent. This was right on an axis, so I didn't have to do anything like that fancy. Okay. This left-hand part will stay exactly the same with the exception of the exponent. The right-hand part is different in every problem. All right, now let's do this left-hand side out. Can someone tell me what you would get using DeMoivre's theorem if you raise this left-hand side to the 4th power? Yeah.
Be r to the 4th,
Mhm.
cosine 4 theta, plus I sine 4 theta.
Yep. And a lot of times when we do problems like this, I just jump right to this step. If it was raised to the 5th power, it would be r to the 5th and a 5 theta. If it was raised to the 3rd power, it would be r cubed and a 3 theta. So that's the step I usually jump right to. But what you're doing is DeMoivre's theorem to get from here to here. Okay, and all this stays the same. All right, so now you have a left-hand side and a right-hand side. You need to solve for r, and you need to solve for the theta. Well, to solve for the r, you have to look at what it's equal to on the other side and find a number that you could fill in for r that would make what's in this red box match that red box. You want them to match because there's an equal sign between them. So what you have to figure out now, this is for the radius. Set the radius on the left equal to the radius on the right, and then solve. Now you're going to do the same thing for the angle. You have an unknown angle on the left. You have a known angle on the right. Set the unknown angle equal to the one that you know and solve for theta. And that will give you your angle, because you have to make what's on the left match what's on the right. There's 2 things on the left, a radius and an angle, and there's 2 things on the right, a radius and an angle. So you're setting up 2 equations to solve for each one of them. Let's put this over here. So we have 4 theta equals 0. Now we're doing a 4th root. And I said this earlier. How many different answers did I say there would be? Yep. 4. Well, the 4 different answers are going to come from there. They're going to come from the angles, plural. When you're solving for roots, you're only going to get 1 radius. But you're going to get multiple angles. And the way you get multiple angles, you have to go like this. You set the angle on the left equal to the angle on the right, but you have to put plus 360k. Why 360? Because if you add 360 to an angle, it doesn't change. We've talked about that. You can add and subtract 360, and it doesn't change the actual answer to your problem. So you have to set the angles equal to each other and put a plus 360 there. Now, it would be nice if I just have theta equals. I'd rather not have a formula for theta. So what would I do to get theta by itself? Yep. Yeah, just divide everything by 4. There's your formula for your angles. So now you might be wondering, well, wait, what's this k? Like what does that mean? K is an integer. It's multiple integers. It's every integer from 0 up to 1 less than your root. So k goes from 0 up to 1 less than the root. So we're doing a 4th root. You're going to plug in 4 numbers for k to get the 4 different answers. The numbers you're going to plug in, 0, 1, 2, 3. That's how you get the 4 answers. So in this case, k equals 0, 1, 2, and 3. So we have our formula for our angle. We'll plug in the values for k in a minute. We have our formula for the radius. We need to solve that. What can you raise to the 4th power and get 1 as the answer? Yep. 1. That's going to be your radius in all the different answers we write. Let's write out all our answers. We're going to have the k equals 0 answer. K equals 1, 2, and 3. Every answer is going to have a radius of 1. So technically, do you have to write it? No. But let's just write it. I'm going to copy and paste that for every answer. And then all I have to do is fill in whether k is 0, 1, 2, or 3. Let's put that. Make a copy. And one more. That, make a copy. Alright, so first one, k equals 0. What's 90 times 0? Yeah. 0. Plus 0. 0. So that is your first answer for the 4th roots of 1. Next answer. K equals 1. What's 90 times 1? Yeah.
90.
Plus 0?
90.
90. Here's your second answer. Bless you. What's going to be my angle for my 3rd answer? Yep. 180. What's going to be my angle for my last answer? Yep. 270. And we can take and convert those to standard form if we wanted to, do without. But we're going to just leave the answers in trig form. All right, so that's the basic process of finding a root. You've got to set up the 2 equations and then find your angles. But the radius is the same every time. 1, 1, 1, 1, 1. They're all ones. And the original direction said to graph it. I didn't really want to focus too much on the graphing. But if you graph these points, this one's has a radius of 1 and it's at 90 degrees. That's the top one. K equals 2 has a radius of 1, but it's at 180. K equals 3 has a radius of 1, but it's down at 270. And the first one had a radius of 1, but it was at 0. Notice how those answers are spaced? When you graph all your answers, they're always equally spaced. So if you do a fourth root and you connected all your answers, you'd get a square. If you did a cube root and connected all your answers, you'd get an equilateral triangle. If you did a fifth root and connected all your answers, you'd get a pentagon, perfect pentagon. So your answers are always equally spaced. That's what happens when you graph. And if you did 2, like a square root, well, you just get 2 in a straight line. That's all you get. All right, so let's try. I'll try another one. All right, let's try this one. Find the fifth roots of 1 plus I. All right. What's the first thing you have to do with that entire equation? Yep.
Put it into trig form.
We got to get everything into trig form, and everything means 2 things. The z, which you put the same thing in every time, and the 1 plus I. Let's start with the z. And you want to think they could tell me what I would have on the left if I change z to trig form and then raise it to the 5th power at the same time. Yep.
R5 cosine 5 beta plus I sine 5 beta.
Yep. So this is really just setting up what you're going to set the radius equal to. So it's going to be r to the 5th equals something. I don't know what yet. And I'm going to have 5 theta equals something. I don't know what yet. That's what I need to figure out, which goes on the other side. But any question on just starting this off to get these 2 equations ready? All right, now we have to figure out what goes on this side. This is what is different in every problem. 1 plus I. Let's graph. Right one, up one. What would be your radius of 1 plus I? Yep.
1.
Well, if the sides are 1 and 1, the hypotenuse has to be longer than 1 because it's always the longest side. 1, 1, 1 would be equilateral.
Got it.
Yep. Square root of 2.
Yeah.
Okay, so I know what I'm setting my radius equal to. It has to equal the square root of 2. Okay, I'll finish that in a second. Now let's get our angle. What's angle going to be right there? You could do inverse tangent if you need to, but this is an isosceles triangle. And it's a right triangle. Yep.
45.
So your angle is 45. Technically it's the inverse tangent of y over x, but that will come out to 45. So there's my angle. Now, I know what to set 5 theta equal to, 45 degrees. Plus, what do I put on the end to make sure I get all my different answers? If I'm doing it in degrees. Yep.
360K.
I'm going to put a plus 360K. If I wanted to do it in radians, I could do a plus 2 pi k. All right, and just so we remember, what are the values that k is going to equal here? You want to get 5 answers. Yep.
0, 1, 2, 3.
0, 1, 2, 3, 4. There's your 5 answers.
Is that always true?
You always go from 0 up to 1 less than that number. Yep.
Oh.
So if we were looking for 8 answers, we'd go 0, 1, 2, 3, 4, 5, 6, 7. There's my 8 answers. We're not going to do 8.
Can we divide it by 5 like we divided the last one?
Yeah, we're going to divide by 5 now. Yep. That was the next thing I was going to ask. So let's get theta by itself here. By dividing everything through by 5. What's 45 divided by 5? 9. So 9 degrees plus 360 divided by 5, 72. Okay, so there is your formula for theta. And now, let's just solve this. To make it, at least I think it's a little easier for me this way, right? A square root is the same as to the 1/2 power. I'm trying to get rid of this 5. When you have a power to a power, you multiply. So what could you put as another exponent right here? So when you multiply power to a power, this 5 cancels out and becomes a 1. Lindsay?
Is it 0?
You can't raise each side to a 0 power because that wipes everything out. It's kind of like multiplying both sides of an equation by 0. You can't do that. But because you're going to have a power to a power, so you want to do something times 5, so you end up with just r. Yep. 1/5. Raise each side to the 1/5 power. Now power to a power, you multiply your exponents together. 5 times 1/5 gives you r to the 1. You just got r by itself. And what do we have here? 2 to the 1/2 to the 1/5. What's that? You can just leave it as a fraction in the exponent.
2 to the 1/10.
That's 2 to the 1/10. Yep. Oh, so there's your radius, 2 to the 1/10. All right, let's get our 5 answers ready. A equals 0. A equals 1. A equals 2, 3, and 4. Okay, I'll put them in those boxes. Okay, 2 to the 1/10. That's going to be the same radius every time. So 2 to the 1/10 cosine plus I sine. Let's take and it's just going to be quicker if I just write it. 2 to the 1/10 cosine I sine. 2 to the 1/10 sine. 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 And 2 to the 1/10 sine. I sine. Okay, now we're going to fill in all the angles. So remember, k equals 0 through 4. Okay, start with 0. What's 72 times 0 plus 9? 9. All right. What's 72 times 1 plus 9? 80 what? 81. And now all you're doing each time is adding another 72 to the answer. So what's 81 plus 72? 156? 153? All right. Add another 72? 225? All right. And add another 72. 297. 297. Now, add another 72. 369. That's 9. You're back at the beginning. So if you add 72 too many times, you're just gonna repeat your answers now. Okay, because 369, if you minus 360, you're back at 9. Alright. So I think once you get used to it, it's not too bad. It just gets annoying when you have 4 or 5 because you gotta write it that many times. But that's the general setup every time. Any questions on that? All right, so I have a list of test topics and the homework for today. Okay, so that's the homework on 458. Let me put the test topics in the video. And those are the list of the different topics that you'll see on the test.
Is that in the video?
Yep, that'll be in the video. So the test will cover law of sines, law of cosines. There'll be one word problem about law of sines and cosines. Converting complex numbers to trig form and back the other way. And the 4 operations we covered yesterday and today. Multiply, divide, powers, roots. The test will have 10 questions, but a law of cosines problem could have 3 answers.